You've seen how to add, subtract, multiply, and divide polynomials. In this video we'll look at ways of factoring or expanding polynomials that rely on polynomial identities. Let's first discuss what an identity is. An identity is a special type of equation that is true for all values of a variable. This is the simplest identity, x equals x. No matter what value you plug in for x, the equation is always true. Usually when you think of an equation with variables, what probably comes to mind is an equation where you are solving for the variable. These types of equations are called conditional equations. They're conditional because they are only true for certain values of x. In this example, the conditional equation is true when x equals 5. Identities are different from conditional equations. Polynomial identities allow you to write a polynomial in a different form, usually to simplify the polynomial or solve an equation. Let's look at some examples. This first example is one that you're quite familiar with, but you probably haven't been shown this as an example of an identity. The distributive property allows you to write a polynomial identity. The expression on the left has a 2x term outside the parentheses. We distribute the 2x to all the terms in the parentheses to get a new expression. As a result of the distributive property, we have a polynomial identity. What this means is that when you see an expression like the one on the right, you can factor an expression to create the same identity but with the sides switched. Let's look at another example. When factoring some polynomials, it will help to know what the square of a binomial looks like. The expression on the left is a binomial raised to the second power. The expression on the right is the terms written out in expanded form, which is an example of binomial expansion. Notice several things. See the 4 here? We double it to create the coefficient of the linear term. Now look at the constant term. It is the square of a 4. Here's another example with the binomial x plus 5 squared. Notice that the coefficient of the linear term is twice the value of 5 and the constant term is 5 squared. So, when you see a quadratic binomial, look for a pattern in the coefficient of the linear term and the constant term. If it can be written this way, then it can be rewritten as the binomial squared. Let's look at another polynomial identity. This one is called the difference of squares. When you have the product of binomials in this form, then the product is the difference of squares, as shown here. In this example, the product of the binomials x plus 5 and x minus 5 is equal to x squared minus 25. Likewise, when you see a polynomial that is the difference of two squared terms, and x squared minus 25 can be rewritten as x squared minus 5 squared, then the polynomial can be factored as the product of two binomials. Here are two polynomial identities you should learn, namely, the sum and difference of cubes. In the first identity there is a difference of cubes. Note that 27 can also be expressed as 3 cubed. The difference of cubes can be expressed as the product of the linear binomial and quadratic trinomial. The sum of cubes has a comparable identity. Now let's look at examples of using these polynomial identities to solve problems. The area of this square is the quadratic binomial shown. Since a square has equal side lengths, then this polynomial should also be able to be expressed as a linear binomial squared. Let's look at this quadratic in more detail. The quadratic can be rewritten this way. Notice that the coefficient of the linear term is 2 times 8, while the constant term can be written as 8 squared. As a result, we can write the area as the binomial x plus 8 squared. Let's look at another example. This part of a roller coaster can be modeled by a polynomial that is the sum of cubes. Find the equation. What you see here is the general form of the sum of cubes. Basically, what we're looking for is the value for a. First, notice that the graph of the cubic function intersects the x-axis at x equals -3. If we write it in this form, x plus 3 equals 0, then the binomial x plus 3 is a factor of the cubic. With this, we can now write the full polynomial as shown. Try graphing both versions on a graphing calculator and you'll see the same shape as the one you see here.